All right, in the last section, we talked about Darwin, his theory of evolution, natural selection, and the main ideas that kind of were surrounding that, and how the interaction of the organisms with the environment um, kind of result in the evolutionary changes that we see. So the first thing I want to start out with is having you guys kind of use your computer, your phone, your tablet, whatever, and go to the OpenStax biology text. So you might have to Google this, Google OpenStax biology. And then I want you to go through and find the section on evidence of evolution. And once you're done kind of reading through that, follow those two learning links and complete one of the activities. And then read over those couple of misconceptions, those types of things. And then what we're going to do is we're going to talk about these in class, okay? So now as far as homologies go, homologies in the tree of life are very important in explaining how ancestry is kind of, how all of these organisms are related to one another in one way, shape, or form. And the greater number of homologies shared by a particular set of species, the earlier on in the natural history of this organism that it's developed, the further down the tree of life. For instance, you'll see in a few minutes that many organisms share Hox genes that kind of lay out the body plan and how these organisms survive, and the fact that they've been highly conserved throughout geologic time, throughout evolutionary time, for hundreds of millions of years, shows how important they are to the development of the particular type of organisms. Homologies that evolve really more recently are only seen in a small branch of the tree. So the more organisms that share them, the further back in time they've evolved, the more, specialized these homologies become, the sooner you'd say, or the more recently they've developed. And if you look at tetrapods, these are four-limbed animals. This is a vertebrate branch of the tree, really, that consists of birds, amphibians, mammals, reptiles, etc. And they all have a very similar five-limb structure, or five-digit four-limb structure, rather. And this indicates that these types of mammals, for instance, in this case, all share a very common ancestor. Okay, so if we look here, we've talked about this a little bit in class, and we're looking at like a human, cat, a whale, and a bat. You can see that you go that one bone, two bones, many bones, and then digits theme. And all of these organisms come from are mammals, for instance, but they all have a slightly different four-limb structure based on their particular environment. And through evolutionary time, that original structure, as these organisms kind of radiated out into different niches, these organisms kind of underwent some selective pressure that resulted in the changes that you're seeing here. Okay, so these similarities, we say, result from a common ancestor. We refer to them as homologies. And, that four-limb structure that we were just talking about is a great example. And this is a structure-function relationship that, even though they have a vastly different function, for instance, flying versus swimming versus, say, grasping things, they all evolved from a common ancestor, and they have a very similar anatomical structure to them. Okay, and the organisms that lack them fall in a different lineage, and we don't share a common ancestor with them. So here's a little video that we can watch that kind of explains what we've been talking about a little bit in class, okay?
The basic pattern for limbs had been in place for millions of years.
Here we have the fin of a 370 million year old fossil fish and an arm of a human. In a human arm, what you have is one bone, then two bones, the wrist, and the digits. In this fin, what do you have? You have one bone, two bones, even little bones that can be compared to a wrist, and then rods that face away from the rest of the appendage itself, just like our fingers or toes. So you have, in a fish fin, already set up about 370 million years ago, many of the bones that are used in a tetrapod limb.
With the basic pattern already there, the fin-to-limb transition took place in a series of small changes occurring over millions of years.
Okay, so what that video was showing really was Neil Shubin. He was that man that was speaking there. He was the guy that was kind of looking for that kind of gap in the fossil record that went from tetrapods to the I guess ancient tetrapods, if you want to think about that, to the modern tetrapods in this theme of the one bone, two bone, many bones and digits. And he was the one that found it, after looking, way up in northern Canada and doing a whole lot of detective work. And he wrote a book on it that was very well written and very interesting to show how really a bunch of different branches of science were used to kind of arrive at the conclusion that he was just explaining to you. He had to use the geological record. He had to use the basic biology of showing these different organisms, possessing these different things, and kind of finding different lines of descent that led back to really the fossil that he had found. So it was quite interesting. All right. So those homologies, again, variations from this common ancestor, this idea that we've been discussing here. And then there's also, it's important to note that there is a lot of molecular homologies that exist as well. So when you start looking at the DNA of these particular organisms that have these different themes, you find lots and lots of similarities in certain genes that are governing the formation of these limbs. For instance, the bat wing versus the human hand and arm, upper appendage, etc. So looking at these things, you could explain how the development occurred. Looking at the Hox genes that we talked about earlier and how those lay down the basic body plans of a variety of different animals, and the different segments associated with those animals have the same, if not exactly the same, very, very close to the same order of A's, T's, C's, and G's that kind of lay down this body plan. So underneath this video segment, you're going to see a link for video 4, and this is going to kind of go through the entire process of explaining how scientists have determined a lot of these different types of molecular homologies that have occurred here, and take you through some of the detective work that was involved and some of the implications of what they found, and the different types of ways in which they showed that these things arose way back in time, and they're carried in a variety of lineages of organisms, and they're all performing the same type of a job. So once you guys have watched that, we're going to discuss this, this in class as well. Okay, so make sure you follow the link and watch the video. And of course, as always with all of these, if you have any questions, make sure you write them down and we'll discuss them in class. Okay, so we'll see you soon.